In this video, I'm going to walk you through the conditional statements notes. So the first part of your notes says a conditional statement symbolized by this, and the way that you read this is P, then Q. Okay, so I'm going to start the statement over again. A conditional statement symbolized by P, then Q is an if-then statement in which P is a hypothesis and Q is a conclusion. Okay, the conditional is defined to be true unless a true hypothesis leads to a false conclusion. A truth table for P then Q is shown below. I'm going to show you how to fill this table out. Okay, so what this table says is if P is true, if you look in the first row here, and it's saying that the hypothesis P is going to be true and the conclusion is going to be true. If both of those statements are true, then what can we say about P then Q? And the answer is that it's going to have to be true if both P and Q start off as true. This right here is the exception that the opening statement was talking about. If you have a true hypothesis and a false conclusion, you're going to be left with a false conditional statement. Okay. In the third row, if you start with a false hypothesis and end with a true conclusion, you will have a true conditional statement. And last but not least, oh, I'm sorry, that's wrong. No, that's right. I'm sorry, I'm going crazy. That's true. And then the very last row, if you have two false statements, it actually becomes true. Just like if you have a negative and a negative together, it makes a positive. So that is your truth table for the conditional statements. In the first example, it says to identify the hypothesis and the conclusion. The hypothesis is the statement that comes after if. So in this case, I do my homework. That is your hypothesis. And your conclusion is the then part without the then. I get my allowance. That is your conclusion. For the second example, it says you've got two statements and write them as a conditional statement. So the first part is an if part. So if the sun is made of gas, then 3 is a prime number. This actually makes absolutely no sense, but this is a conditional statement. Okay, the third one. What is the truth value of P then Q? So when we take a look at P here, 8 is odd. Is that a true statement or not? And it's of course false. 9 is composite. That is true. 9 has more than one pair of factors, 3 and 3 to be exact. So that is a true statement. If I look back up in my truth table, if I start with a false hypothesis and end with a true conclusion, I am left with a true conditional statement. That is the truth value of P then Q. Example 4 is using the same information, but this time is what is the truth value of Q then P. So in other words, I start with a true statement and end with a false statement. That would lead to a false conditional statement. So the answer to number 3 is true. The answer to number 4 is false. Okay, the next part of your notes reads, a biconditional statement is defined to be true when both parts have the same truth value. The biconditional operator is denoted by a double-headed arrow. The biconditional, here's what goes in the blank, P, if and only if Q, that's how you read that double-headed arrow, if and only if. So the biconditional P, if and only if Q, represents, and here we go, we write it out, P, if and only if Q, where P is a hypothesis and Q is a conclusion. The following is a truth table for the biconditional P, if and only if Q. Before you start filling the truth table, here's a small little note. Another way to write if and only if is IFF. That is a universal notation for that we don't have to write the whole thing out. So let's take a look at that truth table. Okay, so in this truth table, P then Q represents our conditional statement. So this is our conditional. Q then P represents the converse. And then P if and only if Q represents the biconditional. Okay? So in order for a biconditional to be true, the conditional must be true and the converse needs to be true. That's how you make a true biconditional statement. So in the first column, we have P being true and Q being true. That's going to lead to a true conditional statement. Okay? It's also going to lead to a true converse, and therefore a true biconditional. In the second row, I start with a true hypothesis and end with a false conclusion. This leads me to a false conditional statement. However, when this is reversed and I do Q then P, I have false then true. That leads to a true converse. The biconditional, however, is going to be false because the conditional and the converse do not match. They have to both be true in order for the biconditional to be true. Third column, start with a false hypothesis, end with a true conclusion. We get a true conditional statement. If I reverse this and get my converse, I have a true statement, then a false statement. That leads to a false converse. If my conditional is true and my converse is false, my biconditional is false. In the last row, I start with two false hypotheses and conclusions, which leads to a true conditional statement, which will also lead to a true converse. Since both of those are true, my biconditional will be true as well. All right, let's take a look at those examples. So example 5 says, write A if and only if B as a sentence, then determine the truth value. So we start off with the first statement, which is x plus 2 equals 7. So x plus 2 equals 7. And then I do if and only if. And then I write my second statement, x equals 5. So we have to determine the truth value for this. So we have to check the conditional and the converse. So here's my conditional statement. I would write if x plus 2 equals 7, then x equals 5. Is that a true statement? Yeah, sure, why not? That's a true statement. If x plus 2 is 7, then x is equal to 5. Let's switch that up and see the converse. If x equals 5, then x plus 2 equals 7. And that is also true. Therefore, what can we say about the biconditional? And the answer there is that is going to be true as well. Number 6, is this sentence biconditional? X plus 7 equals 11 if and only if x equals 5. The sum of 5 and 7 is not 11. It's actually 12. So there's a falseness in here somewhere. The way that we figure that out, again, is to look at the conditional and the converse. The conditional statement would be if x plus 7 equals 11, then x equals 5, which is false. The converse of this is if x equals 5, then x plus 7 equals 11. And that's false as well. So if I've got a false conditional and a false converse, there's no way I can have a true biconditional statement. So that the biconditional is going to be false. All right, number 7, is this statement biconditional? A triangle is isosceles if and only if it has two congruent sides. We have to write out the conditional and the converse. So the conditional is going to be if a triangle is isosceles, then it has two congruent sides. Is this true or false? This is actually a true statement. Okay, isosceles triangles do have two congruent sides. So let's reverse this statement. If a figure has two congruent sides, then it is an isosceles triangle. Is that true? It could be, but is it absolutely true? Absolutely not. There could be any number of shapes out there that have two congruent sides. It does not have to necessarily be an isosceles triangle. Therefore, this statement is false. Therefore, the biconditional is false because the conditional and the converse have true and false statements. All right, last part. So the next part is a good definition has several different components. The first thing is it uses clearly understood terms. That's what goes in the first blank. Is precise. Avoids words such as large, sort of, and almost. What large means to me may mean something different to you. So you don't want to use words that can be determined just by a different perspective, okay? If I mean sort of, that might mean something different to you. If I say almost, that might mean something different to you than it does to me. So we want to use precise words. The last thing, that it's reversible. In other words, we can write it as a true biconditional statement. So in example 8, it says, show that the definition of perpendicular lines is reversible, then write it as a true biconditional. So this is showing you that what a good definition actually is. So here's the definition. It says perpendicular lines are two lines that intersect to form right angles. Here's our conditional statement. We're going to say if two lines are perpendicular, then they intersect at right angles. Okay? That's a true statement, so we're good so far. Okay? If two lines are perpendicular, then they intersect at right angles. That's true. How about the converse? Let's see that. If two lines intersect at right angles, then they are perpendicular. True or false? That's true as well. Therefore, I can write a true biconditional statement since both of those are true. And it's going to look like this. Two lines are perpendicular if and only if they intersect at right angles. Okay? So if you can write the conditional and converse both as true statements, you can therefore write it as a biconditional statement, and that makes a definition a good one. So let's take a look at the last three examples that we have here. All it asks is, are these good definitions? All right. First one, an airplane is a vehicle that flies. You first of all have to ask yourself if it's reversible. So if I were to write this as a conditional statement, I would write, if it is an airplane, then it is a vehicle that flies. Sure, that's fine. Okay, reverse it and let's see what happens. If it is a vehicle that flies, then it is an airplane. That is not a true statement. If it's a vehicle that flies, what other options are there? We could have a blimp, we could have a helicopter, some other people were saying it could be a flying car, it could be anything. So what we're going to do is we're actually going to write a counter example that shows where this definition is false. So one example could be a helicopter. Okay. So the next one, a triangle has sharp corners. So if it is a triangle, then it has sharp corners. That's true. But now we have to reverse it to see if it's a good definition. If it has sharp corners, then it's a triangle. That is not true. Let's figure out a counter example. What else could have sharp corners? Well, I could say it could be a square. rectangle, hexagon, anything like that. The last one, a square is a figure with 4 right angles. So if it is a square, then it has 4 right angles. So that's a true statement, but now we have to reverse it. If it has 4 right angles, then it's a square. Can you think of what it is? What is my counterexample? What is the other figure with 4 right angles? And it would be a rectangle. That concludes the notes. Please start on your homework.